We have been looking at the S densities of arbitrary subsets of Rn and discussed some basic bounds on the densities. And in the previous video, I gave the proof from Mattila's book about those bounds. Part of the theorem there was saying that almost everywhere outside a set, the density is zero. This one has a simple yet very important corollary, which says that when you restrict to a subset, on the points of that subset, the density doesn't change. And intuitively, this can be justified by, again, comparing to the Lebesgue density point. Almost every point in F is a density point of F. Again, I'm thinking about Lebesgue density theorem. That means the balls are almost completely contained in F, which makes them also completely contained in E. So there is only a negligible number of points where you have lost the density. But the proof of this is just applying the theorem from above to the set E minus F. I'm also carrying over the assumption that the HS measures here are finite, because that was necessary in that theorem to begin with. And that's basically the end of the proof, because it's a matter of just set theory. So E intersection with a ball, you just compare it to E intersection, F intersection with that ball. And E minus F intersection with that ball. Now the theorem said that this part measures theoretically is negligible, so that makes this equal to that, but that is just density of F versus density of E, both evaluated at the point X. So what are the consequences of this one? For that, we have to look at how Falconer looks at the sets. So Falconer's book called The Geometry of Fractal Sets. This book came a few years earlier than Mattila's book, and Mattila also references that for many things. It's a smaller book which deals mostly with planar sets, subsets of the plane, but also does it in great detail and gives a lot of commentary on how things work or don't work in higher dimensions. It's a beautifully written book, so easy to follow, and I find that the details in this book are often more than I've seen in any other geometric measure theory book. So definitely check that out. But what I am borrowing from Falconer's book is that he defines, S sets. So S again is some real number, and an S set in Rn is some HS measurable set E of Rn with HS of E being finite and strictly positive. And this is justified by the fact that, well, if you look at HS equal infinity, maybe E is not even an S-dimensional set, so allowing infinity is just useless. And if HS of E is 0, then we don't get any interesting results, because most of our results in geometric measure theory are like, up to a set of measures 0, your set has this property or that property. Density is this way almost everywhere. But if HS of E is 0, then all those claims become trivial things, because the whole set has 0 measure. Therefore, this is very natural definition. So This is called a set. Then it follows by the definition of regular points of a set. So x in E is regular for an S set if the, okay, so upper and lower S densities defined above both equal the value of 1. Over the course of videos, I've emphasized this deep fact from geometric measure theory that just the fact that upper and lower density of a set exists, that means they are equal and finite, is a huge requirement for a set. And the latter part, both being equal to 1, is actually not that restrictive. Again, it is true that if the densities, if upper and lower density agreed almost everywhere, then the common value would be 1. So how does the corollary come in here? Given this S set E, let E, say R, be the set of X in E that are regular, and then EI, those in E that are not regular, so the irregular part. The fact that we haven't mentioned, well, the densities are measurable functions of X. So if X changes, then those functions change measurably. That we haven't talked. The proof is in Falconer's book again. Mostly the proof is because it's defined through fractions, and instead of r going to 0, we can select r to be 1 over k, and k goes to infinity, so you have a countable limit, and each single fraction then would be, when you freeze k, will be a measurable function, so the limit also is a measurable function. So these are very standard tricks in proving measurability of objects. But anyway, from those it will follow that ER and EI are measurable. So here we're talking about HS. So these are measurable subsets of the set E. And HS of E is finite by being an S set. Therefore, the corollary applies, and we get that. So the corollary implies then that ER itself is made up of only regular points. Well, it's always up to measure 0. So this is, in other words, saying that almost every X in ER is a regular point of ER. And then we call such sets just S regular. It's an S set, and almost every point in it is regular. Okay? And again, similarly, we get that EI is not S regular. Well, it's more than that. No point is there. So EI is irregular. That is, almost everywhere density is not, either does not exist or is not equal to 1 when it does. obviously E is ER union EI. So what we ended up is a decomposition theorem that studying Ssets, this part is not restrictive, just finite and positive HS measure, can be done separately for regular and irregular ones. So that we don't have to always talk about the sets where at some portion of the set we have regularity and at some other port we don't. So we can completely separate the analysis. If you want to make some geometric claims about regular sets, we can just separately study that, and then for the irregular ones we again study them separately. Because of this decomposition, we get the full picture. As I have mentioned in the video dedicated to Marstrand's theorem, that indeed we can never have regular S-regular sets unless the S is an integer. And this is a very remarkable deep theorem of Marstrand. So when S is non-integer, we can only talk about the irregular S sets. And 2 chapters of Falconer's book are dedicated just to study of one regular sets in R2. And the following chapter is dedicated to study of S between 0 and 1 S sets in R2, and this fact that S regular in this case cannot be S sets cannot be regular is proven in that chapter, and for this we get this another fundamental result, that one regular set is necessarily a rectifiable one, so it's contained in a countable union of rectifiable curves. So existence of density makes your set as close to being a curve as one could wish. Okay, so I will reference Falconer's book more and more because I found the exposition there kind of more concrete and explicit and easy to follow, mainly because he's only concerned with the planar subsets and presents the theorem in lower dimensions for clarity. By the way, that's how Besikovic actually started the whole story. He also focused on just planar subsets. That doesn't mean necessarily, by the way, that it's any simpler than arbitrary dimensions, and already the fundamental ideas there help do the higher dimensional analogs. So if I ever get to cover any of the things I discussed here, even for one-dimensional one sets here in this terminology, one sets inside plane, I will be completely satisfied. So hopefully more videos coming in this direction, but before that I have other stuff that I will need to cover again from Mattila's book. So a huge of course body of research and a lot of classical results in geometric measure theory. There is no end to it, but we try to just present you with some of the deepest and most elegant results, so that hopefully you find this theory something that you can be working on in your future career. Thank you for watching again today, and have a nice day. Thanks a lot.